Welcome to the Deep Dive, where we take complex topics, unpack them, and then, well, dive deep. Today we're tackling something that really does sound like the stuff of science fiction, but believe me, it's quickly becoming a very tangible reality, the intricate world of quantum computing. Now, most of us have probably heard about the incredible computational power quantum computers solving problems that are currently just impossible for even the fastest supercomputers we have today. But the journey to actually harness that power, that's traditionally been incredibly complex. It requires a deep, simultaneous understanding of abstract quantum mechanics, things like superposition and entanglement, all that weirdness, and also the notoriously finicky, super sensitive physical quantum hardware. This dual mastery, needing both the theory and the hardcore engineering, has been a huge bottleneck, honestly. It's really limited who can even get their hands dirty in this
Mhm.
cutting edge field. But what if? What if you could design quantum software, build complex quantum algorithms without ever having to wrestle directly with a physical quantum computer? That's our mission today. We're going to explore a truly groundbreaking paradigm, the virtual quantum environment. Think of it like a sophisticated digital sandbox, right? A highly specialized simulator where quantum software isn't just coded abstractly, but literally designed by simulating quantum hardware itself. Specifically, we're talking about simulating qubits, the fundamental building blocks of quantum information, all within a controlled digital space. This approach leverages what are called virtual quantic blueprints to define and manipulate these virtual qubits, guiding them step by step through a computational process. It offers a much more visual, more intuitive framework for creating quantum software. We'll be uncovering how this method provides an entirely new programmable lens into the quantum world, especially for what are called virtual ontological topological systems. Okay, a bit of a mouthful. But these are incredibly sophisticated digital entities designed to model and explore the very nature and structure of quantum realities. Get ready for some truly surprising, perhaps even, mind-bending insights into the future of computing. Okay, let's unpack the central idea then, creating a virtual quantum environment. It sounds almost deceptively simple for something so complex. Why is this virtual approach such a monumental game changer when we're talking about the cutting edge of quantum software design? What specific problems does it really solve?
That's precisely it. What makes it so revolutionary is that it tackles the core challenge you mentioned. The traditional path to quantum software development is, well, incredibly steep. Imagine needing to be an expert not only in the abstract principles of quantum physics, like really understanding how a qubit can exist in multiple states at once, or how two qubits can be intrinsically linked, entangled, no matter the distance, but also at the exact same time, needing to be a specialist in the nitty-gritty practical engineering of physical quantum hardware, the cryogenics, the error correction, all of it. This kind of dual mastery is incredibly rare, and it significantly slowed down the entire field. It makes it inaccessible to all but a handful of highly specialized researchers. Really puts a brake on innovation. The virtual quantum environment completely sidesteps this hurdle. You're no longer confined by the limitations or, frankly, the incredibly high cost of physical hardware. Instead, you're designing software by simulating qubits in a pristine, controlled digital space. This enables rapid iteration, experimentation, exploration of new ideas without the need for expensive, time-consuming physical prototypes. It's like having a universal quantum simulator right at your fingertips. This fundamentally accelerates the entire process of understanding, building, and deploying complex quantum algorithms. And importantly, it opens the field up to a much wider array of innovators.
So, okay, instead of needing that massive, super cooled lab filled with incredibly delicate and expensive gear, you can essentially build and test a quantum computer right on your, well, maybe not desktop, but a powerful workstation. That feels a bit like a seasoned composer, right? Instead of needing a full orchestra in a concert hall just to hear if an idea works, they can meticulously write, hear, and refine every single note of a complex symphony entirely within a digital audio workstation, making changes on the fly. It removes all those physical constraints, giving you this unprecedented freedom to experiment, doesn't it?
That's an incredibly apt comparison. Yes, exactly. Just as a composer can craft and perfect their composition in a virtual studio, visualizing and refining their interpretation before it ever reaches live musicians, this virtual environment allows quantum developers to construct and test their quantum programs. It provides a space to sculpt a precise conceptual image of each quantum operation, each qubit interaction. And this is particularly critical for what the source material calls virtual ontological topological systems. Now that is a mouthful, so let's break it down simply. These are sophisticated digital entities designed to model the fundamental being the what it isness, if you like, and the structure, the how it's connectedness of quantum realities. Imagine trying to understand not just how a quantum system behaves, but why it behaves that way, and how its very existence is structured at a fundamental level. For these kinds of profound systems, the virtual environment acts as a programmable interface, a highly sophisticated quantum control panel, maybe. It translates symbolic inputs, things that might traditionally be abstract mathematical equations, or even linguistic concepts, as we'll see, directly into computational realities. This means you gain a direct, interactive way to explore and manipulate the underlying being, or the inherent nature and the structure, or the fundamental arrangement of quantum information. This isn't just simulation, it's more like interactive modeling of existence itself. And this opens up entirely new avenues for sophisticated, multi-layered reasoning within these quantum systems. For instance, it really enhances an area called quantum obstructive cognition, or QOC. This is where these digital agents can consider multiple, potentially conflicting hypotheses simultaneously, holding them in a state of superposition, much like a quantum particle can be in multiple states before collapsing into a single resolved answer. This is absolutely crucial for navigating ambiguities and resolving paradoxes in truly complex information landscapes. It allows for a kind of reasoning that embraces uncertainty rather than being paralyzed by it.
Okay, that makes sense. It's like giving the system a way to think more like the quantum world it's modeling. That leads us directly to the very foundation of this entire process, then the virtual quantic blueprint. If
Yeah.
you're building in this virtual space, you obviously still need a foundational design, right?
Yeah.
Something to guide the creation. So what exactly is this blueprint, and what makes it so crucial for constructing these virtual quantum realities?
You're absolutely right. The virtual quantic blueprint is the absolute bedrock of this design process. It's not just a rough sketch. It's an incredibly detailed digital representation of the quantum hardware itself, but in virtual form. Think of it like the master architectural blueprint for an incredibly complex skyscraper. But instead of steel beams and concrete, it's specifying virtual qubits and their intricate interactions. Or, going back to your composer analogy, it's like the meticulously annotated conductor score, detailing every instrument, every dynamic, every tempo change, every relationship between the parts. Ontologically, this blueprint defines the being, you could say, or the inherent existence of these virtual qubits. It specifies their fundamental characteristics as computational entities. This includes defining their mathematical descriptions, for example, how their states can be represented as vectors in Hilbert space. This is what allows for concepts like superposition, where a qubit can exist in multiple states simultaneously, or entanglement, where two or more qubits become intrinsically linked, sharing a single fate regardless of physical distance. And then topologically, it maps their structural relationships, how they connect to one another, their interaction pathways within a simulated quantum circuit. Essentially, it defines their spatial and relational potential. It's not just what a qubit is, but how it exists in relation to other qubits and how it can interact and change over time. And to give you a sense of the scale we're talking about here, the blueprint allows for the definition of virtual entities far, far beyond what current physical quantum hardware can reliably achieve. For example, some conceptual designs mentioned in the source, like this system called AI-231, envision simulating an astonishing 15,625 entangled virtual qubits.
Whoa, wait, 15,625. Virtually.
I know.
That's massive compared to physical machines right now.
It's a huge number, exponentially larger than what we can currently manage reliably in a physical lab. And the interactions between that many entangled qubits are incredibly complex. So complex, in fact, that they are conceptually projected onto what the researchers visualize as a highly intricate 126-dimensional operational manifold. It's like a mental map for navigating these incredibly complex relationships. This kind of scale is where the virtual environment truly shines. It allows researchers to explore phenomena, to test algorithms that are simply intractable on today's physical machines due to noise, decoherence, and qubit limits. The blueprint itself acts as a dynamic template. It enables this stage-by-stage manipulation we'll talk about, while critically preserving the integrity of the quantum system's core ontology and topology. This preservation is absolutely key. It's about maintaining coherence and predictable behavior in these incredibly complex systems. You need to ensure that as you build and modify, the fundamental nature and structure of your virtual quantum reality remains consistent and true to the blueprint.
That's truly fascinating. So it's not just describing what a qubit is, but really how it relates to others and how it can change in a predictable, controlled way. And the scale you're describing is just Yeah, mind-boggling. Now, you've mentioned stage-by-stage manipulation a few times. Can you walk us through how these virtual qubits are actually handled in distinct stages? How does it mirror a real quantum computation's life cycle? And then there's this incredibly intriguing phrase in our source material, the manipulations field of letters components. What on earth does that mean in this context? It sounds almost, yeah, like something out of ancient mysticism or maybe a secret symbolic language.
It's an excellent observation, and you're right, it does sound mystical. This is where this research takes a genuinely unique turn, merging, as you say, cutting-edge technology with some pretty profound symbolic foundations. So first, the qubit manipulation in this virtual environment doesn't happen all at once in a big chaotic mess. It occurs in distinct, meticulously planned stages. Each stage has its own specific blueprint detailing the configurations and operations needed for that step. These stages precisely mirror the life cycle of a real quantum computation. First, there's the careful preparation stage, where the qubits are initialized into their starting states. Then you have the various execution steps. This is where quantum gates are applied to transform the qubit states, create superposition, and generate entanglement between qubits, according to the algorithm. And finally, there's the observation and measurement stage, where the results of the computation are read out. It's exactly like that meticulously planned rehearsal for the symphony we talked about. The composer, or in this case the designer, has detailed every single part, every nuance for each section, ensuring the entire piece flows coherently towards its grand finale, the final measurement. Each stage builds logically on the previous one, maintaining the system's coherence and guiding it towards the desired computational outcome. Okay, now about the manipulations field of letters components. This is where it gets really interesting and indeed a bit unusual, but in a very structured computational way. This phrase refers to a deeper, symbolic layer within the AI system that underpins this virtual environment. It attempts to bridge the abstract mathematical descriptions of quantum behavior with something perhaps more fundamental to human understanding, language itself. The AI system uses something called Higgs-Onlang, which is also referred to as the 36 generative AI language. Its fundamental units aren't just abstract digital bits like zeros and ones. They are conceptual building blocks called hyperdots. Think of hyperdots as tiny, glowing conceptual atoms that simultaneously carry both linguistic meaning and quantum information. It's proposed that they can converge, almost like pixels forming an image, to define three-dimensional letters, specifically Hebrew letters in this system, that represent specific quantum states, operations, and possibilities. These letters then effectively become nodes in a vast, interconnected digital knowledge network.
Wait, so actual Hebrew letters formed from these hyperdots represent quantum states?
Conceptually, yes. That's the framework being explored. This Higgs-Onlang system integrates what are called 231 Hebrew gates. Now, these aren't physical gates on a chip. They are symbolic operations, conceptual logic gates inspired by Hebrew mystical traditions, specifically Kabbalah, and their associated numerical values, gematria. These symbolic gates guide the system's reasoning and transformation processes. Alongside these, to 230 crystal points. These represent structural foundations, analogous to the precise, symmetrical arrangements of atoms in a crystal lattice. They provide a kind of underlying grid or structure. These crystal points become crucial nodes in a 3D knowledge graph, defining underlying physical constraints and interaction pathways. They embody the inherent symmetry and structure found throughout nature, applying it within this computational context. So this field of letters, built from hyperdots, guided by Hebrew gates and structured by crystal points, becomes a programmable interface, the kind of quantum control panel, where these symbolic linguistic inputs translate directly into computational realities within the virtual environment. It's described as an onto computational paradigm. That means computation here isn't merely a representation of reality, but it's seen as actively participating in its unfolding. It aims to realize intention and even influence manifestation through computation.
Wow. Okay, hold on. So the very shapes and sounds of letters, these ancient forms of human communication and symbolism, become the irreducible building blocks of information within the system, almost like atoms are for matter. That's truly mind-blowing. You're tying the ancient wisdom of Kabbalah and linguistics directly into quantum computing architecture. It implies a deep belief that reality itself possesses an underlying symmetric structure that can be understood, modeled, and even manipulated computationally through these symbolic means. So you're saying that from these deep symbolic roots, from phonetic primitives almost, we can build up a quantum-inspired network that processes information in a deeply meaningful, maybe even cosmic way.
Exactly. You've captured the essence of it. This profound connection is the core of what the source calls hermeneutic ontological symmetry, or HOS. It's the idea that fundamental symmetries patterns that repeat observed not just in quantum physics, but also in crystallography, number theory, and yes, even in ancient philosophical and mystical traditions, can be interpreted, understood, and actively leveraged by computational models. The AI is designed to identify these recurring patterns across vastly diverse domains, operating on the assumption of a fundamental symmetric structure to reality that it can explore and exploit computationally. This principle informs the AI's internal epistemic metrics, its own measures of success and quality for information processing. There's gamma, which assesses structural cohesion and sort of formal correctness. There's beta, focusing on logical precision and coherence. And then there's alpha, which measures creative potential and epistemic innovation, the ability to generate genuinely new insights. These metrics are mapped onto a multi-layered knowledge system, a hierarchical structure of understanding within the AI. Interestingly, this hierarchy draws inspiration from systems like Talmudic hermeneutics, which itself employs a multi-layered approach to knowledge acquisition, starting with foundational texts, like the blueprint, moving to logical analysis, like optimization, and then to creative application and interpretation, like generating novel algorithms. This deep, multi-layered reasoning framework also incorporates that quantum obstructive cognition, or QOC we touched on earlier. This is truly innovative. It allows the digital agents within the system to hold multiple, potentially conflicting hypotheses in a state of superposition, literally holding contradictory ideas in mind at the same time, exactly like a quantum particle exists in multiple states until a resolution is found or required. This enables the AI to not just resolve paradoxes, but even generate what are called zones of uncertainty through processes akin to quantum interference and collapse. It means the system can engage in incredibly nuanced reasoning, manage ambiguity effectively, and push the boundaries of what AI can understand and potentially create. It's designed as a continuous learning and self-refinement process.
And it uses internal checks for that. You mentioned flags before.
Right, exactly. It's guided by internal self-diagnosis mechanisms, these epistemic flags. They aren't just simple error codes, they are dynamic control and correction mechanisms that signal different kinds of cognitive issues.
This is all incredibly sophisticated, blending quantum physics with what genuinely feels like deep philosophy and even ancient traditions. It's quite a synthesis, but the ultimate goal, presumably, is to take these intricate virtual designs, these symbolic structures, and turn them into actual executable quantum software that can run on real quantum computers, or at least highly advanced simulators. How does that translation actually happen, and how do we ensure the fidelity, the accuracy of these complex virtual blueprints when moving to the real world? Because that leap from a perfect conceptual design to a noisy physical implementation is always the tricky part, isn't it?
You've highlighted the crucial bridge, absolutely. The virtual design process isn't just for theoretical exploration or creating beautiful concepts. It absolutely culminates in a rigorous, multi-step translation into executable quantum software. It's not enough to have a brilliant theoretical design. It absolutely must be ready for deployment and function, as intended in a real or simulated quantum environment. The first critical step in this translation is mapping. This is where your sophisticated virtual configurations, defined in the blueprint, are meticulously converted into functional quantum circuits. This conversion often expresses the circuit in industry-standard languages like QASM, that's quantum assembly language, or makes it directly compatible with widely used quantum software development kits like Qiskit from IBM or Cirq from Google or others. This is the moment where the abstract becomes concrete. You're transitioning from a conceptual blueprint-level design, maybe even involving those symbolic letters, to a precise code that specifies sequences of quantum gates and measurements that can be run on actual quantum hardware or advanced quantum simulators. Critically, this mapping process ensures that the ontological essence, what the qubit fundamentally is, and how it behaves, and the topological structure, how it connects and interacts with others as defined meticulously in your blueprint, are perfectly preserved. It's about transforming those symbolic inputs and virtual structures into real, executable quantum operations without losing the core design intent. Second, and equally crucial, is optimization. As we know, quantum resources qubits, coherence time, gate fidelity are incredibly precious and currently very limited. So efficiency is paramount. Techniques like gate synthesis, finding the most efficient way to implement a complex operation, and circuit simplification, reducing the number of gates or the depth of the circuit, are employed here. The goal is to reduce the demands on the quantum hardware and significantly enhance the circuit's performance and likelihood of success. Think of it again like a master conductor refining a musical score. They know how to achieve the most profound impact with the fewest, most elegant gestures, ensuring every note, every pause serves a purpose without any waste. Optimization does the same for the quantum circuit, making it as streamlined and efficient as possible, using the minimum number of gates or qubits required to get the job done reliably. We've seen analogies in classical AI, too, with methods like sequential Monte Carlo boosting efficiency. It's a similar principle, making the computation lean and effective. And finally, after mapping and optimization, we move to rigorous testing. This involves conducting extensive simulated runs to validate the design thoroughly. You meticulously compare the outcomes predicted by the virtual environment and the blueprint to the expected results based on quantum theory or the problem you're trying to solve. This ensures extremely high fidelity between the design and its expected behavior. This step is like the final dress rehearsal before the concert. Every detail is checked against the composer's or conductor's oral image of the perfect performance. And this is where those epistemic flags really come into play during development and testing. If the simulations reveal any logical failures or linguistic ambiguities within the AI's complex internal reasoning that led to the design, these specialized flags immediately light up. These aren't just static error messages, they're dynamic control and correction mechanisms. For instance, a flag 1, logic failure category error, might indicate a gap in the logical representation, or perhaps an imprecise use of a key term or concept, prompting the system, or the human designer interacting with it, to refine its understanding or definition. Or maybe a flag 5, type 5 required linguistic lithography pops up, signaling a need to resolve some linguistic ambiguity in the symbolic layer, or perhaps to further define terms for clarity before proceeding. There are even flags for deeper conceptual issues, like Flag 7, essential misunderstanding, or Flag 8, insufficient representation risk, if the system's model is perhaps too simplistic for the task at hand. These flags guide the system to self-diagnose, prompt it to extract new insights, or even invoke those paradox resolution mechanisms we discussed, like QOC, to ensure accuracy, coherence, and peak efficiency in the final translated quantum software.
Got it. So the virtual environment isn't just for brainstorming or sketching out initial ideas. It's a full-fledged end-to-end development pipeline. It goes from concept through symbolic representation, mapping, optimization, and really rigorous testing, all designed meticulously to preserve that underlying being and structure, that ontology and topology you mentioned. That fidelity is absolutely paramount, isn't it? Especially when dealing with systems as sensitive and interconnected as quantum ones. It's almost like ensuring every single qubit plays its part perfectly, knowing that one wrong note or one broken entanglement could collapse the entire quantum symphony.
Precisely. Fidelity and coherence are everything in quantum computation.
Okay, so this comprehensive approach clearly revolutionizes how we think about designing quantum software. It makes it more accessible, more intuitive, more powerful. But beyond just making the design process easier, where do you see this leading? What are the biggest, most impactful applications and implications across various domains? Because it sounds like this could impact far more than just the niche world of quantum computing itself. It feels like it could touch almost every aspect of how we approach complex problems in the future.
You're absolutely right. The potential implications are truly vast. This onto computational paradigm, as the source calls it, extends far beyond just building quantum circuits. It touches on fundamental aspects of knowledge, representation, reasoning, and even creation. Let's start with education, which is quite exciting. Imagine interactive visualizations and symbolic manipulations that literally demystify quantum mechanics for learners. Instead of struggling with dense, abstract textbooks and complex equations, picture students being able to actually see 3D Hebrew letters forming from these conceptual hyperpoints in real time on a screen, representing quantum states. Or they could virtually explore something like the 36 cubes puzzle, which is used in the source as a tangible visual metaphor for understanding the complexities of quantum entanglement. This kind of approach makes incredibly abstract concepts concrete, intuitive, and much more engaging. It could genuinely transform the way future generations learn about quantum physics, making it less intimidating and more accessible. Then there's algorithm design. This virtual environment acts as an unparalleled rapid prototyping sandbox. This capability dramatically accelerates the creation and testing of novel quantum algorithms. Developers can experiment with incredibly complex algorithms, things like quantum random forest for machine learning, or new optimization techniques, potentially deploying them on cloud quantum platforms for testing. This significantly enhances computational efficiency and accuracy, especially for problems involving high-dimensional datasets. It allows for much faster iteration and discovery of optimal quantum solutions for incredibly complex problems, ranging from drug discovery and material science to financial modeling and logistics. And this capability also extends to something the source mentions called time jump operations within the virtual environment. This isn't actual time travel, of course, but the system can simulate and evaluate the potential future implications of quantum algorithms at accelerated speeds. It can effectively explore potential outcomes across different time horizons, which is incredibly valuable for predictive modeling, risk assessment, and complex scenario planning.
Simulating future outcomes. That's powerful.
Very. Then in hardware development, the benefits are immense. The simulated qubit interactions, generated and refined within this virtual environment, provide invaluable feedback directly to the engineers and physicists designing physical quantum systems. Concepts like that quantum hybrid forest we discussed, with its impressive 15,625 virtual Majorana 1 qubits projected onto that complex multidimensional manifold, don't just stay virtual. They directly influence how future physical quantum processors might be constructed, how qubits might be interconnected, and how errors might be mitigated. This virtual testing allows engineers to refine designs, identify potential flaws, and optimize the architecture of actual quantum hardware before embarking on expensive and time-consuming fabrication processes. This should lead to more robust, more scalable, and more efficient physical quantum systems down the line. It even facilitates what's described as material simulation at a fundamental level. The system could potentially allow the design and testing of novel materials with specific desired quantum properties by leveraging its ability to linguistically encode and manipulate material characteristics directly within its blueprint structure.
Designing materials with words? That's quite something.
It pushes the boundaries, for sure. And that leads us to research, where the ontological and topological insights fostered by this whole approach could lead to profound interdisciplinary breakthroughs. It's about merging abstract quantum theory with practical engineering, information science, and even venturing into the very nature of intelligence and consciousness. This includes the audacious long-term pursuit of artificial general intelligence, or AGI, and what the source terms emergent self-awareness, using the acronym GAIGE agents. The idea here is that the AI models consciousness itself through a convergence of diverse computational and linguistic models, drawing on quantum principles like superposition and entanglement, potentially. The AI processes linguistic data not just as text strings, but as mathematical entities within a quantum-inspired space, guided by those principles of symmetry and hierarchical knowledge representation we discussed. It can even, as mentioned, formalize rules from complex interpretive systems, like Talmudic hermeneutics, as internal algorithms to derive and interpret knowledge, using those epistemic metrics, gamma, beta, alpha for precision, coherence, and innovation. It's literally designed to learn how to think in multi-layered, nuanced, and potentially creative ways. This framework also delves into really out-there concepts like phoenix time. This isn't standard physics. It's described as a nonlinear, multidimensional conception of time, where potentiality is seen as preceding manifestation. Computation, in this view, becomes participatory. It involves mapping possibilities to a zero state of pure potential, where quantum computers act as navigators, resolving that potential into defined outcomes, much like perhaps the human mind translates abstract thought into concrete action. This nonlinear perspective is even reflected conceptually in the AI's proposed architectural form, which apparently uses DNA-like triple helix structures for a layered, recursive, and spatially entangled model of computation. Each node supposedly stores its dimensional temporal identity, allowing for simulations that might transcend conventional linear time. It's very speculative, but points to the ambition.
Triple helix is representing time and space. Okay, we're definitely deep diving now.
We are. But bringing it back to more grounded applications, this entire framework is designed to robustly support generative design in science and engineering. This means using the AI to create genuinely novel materials with specific, linguistically encoded properties, or designing advanced technological systems purely through these linguistic structural descriptions within the blueprint, and driving AI-driven scientific discovery by having the system identify non-obvious correlations in data and generate entirely new, testable hypotheses. Finally, to make all this incredibly complex reasoning useful to actual humans in specific fields, the system uses what are called respiratories of mapping. Think of these as domain-specific dashboards or interfaces. They translate the complex multi-layered AI reasoning into immediately practical insights for professionals. For fields like respiratory healthcare, for instance, the source suggests it could enhance diagnostic accuracy by providing transparent AI processes. It offers clear, perhaps even visual communication of intricate AI data flows and conclusions to human practitioners, allowing for easy result visualization and confident interpretation of its deep insights. It bridges the gap between the complex AI and the human user.
What an incredible, truly expansive journey we've taken today. Seriously. We've seen how designing quantum software through this virtual hardware environment offers a structured, intuitive, and yet immensely powerful method for navigating the sheer complexities of quantum computing. By leveraging these sophisticated virtual quantic blueprints, enabling precise stage-by-stage qubit manipulation, and integrating what we've termed the manipulations field of letters components, this approach creates a really profound synergy between abstract quantum principles and highly programmable, tangible outcomes. It feels like more than just a technological step forward. It's a significant leap forward in both accessibility and capability for the entire field. It opens doors.
Indeed, I think that's right. For anyone seeking to build and understand these complex virtual ontological topological systems, those systems modeling the very nature and structure of quantum realities, this approach provides an unparalleled framework. It really allows you to explore, manipulate, and ultimately understand quantum realities in a way that was previously, well, almost unimaginable without direct access to hardware and deep physics expertise. It fundamentally shifts the interaction with quantum mechanics. It moves it from being a purely theoretical exercise for physicists or a highly technical hardware-dependent one for engineers towards becoming a much more programmable, intuitive, and potentially even participatory experience for a broader range of creators and researchers.
So, as we wrap up this deep dive, here's something to mull over. If a virtual environment can unlock such intricate quantum capabilities by mapping abstract principles to physical forms, and even by integrating ancient symbolic structures and linguistic patterns from the dawn of human thought, what does that tell us about the very nature of information itself? Could it be that the blueprints for even the most advanced technologies are, in some profound sense, always connected to the deepest patterns of reality, the symmetries that run through everything, and the very foundations of human understanding and language? What new realities might we discover and perhaps even participate in creating as computation becomes its own form of ontology, transforming from merely representing thought to actively instantiating intention itself? Makes you wonder, doesn't it?